All right, so today we will be doing homework 2, part A. And so what we're going to be doing today is we're going to be looking at a tubular flow reactor. We can also call that a plug flow reactor. And we're going to be dividing it up into 100 perfectly mixed sections to simulate back mixing. And so we're going to treat each of these sections like one individual CSTR because those are perfectly mixed. And then we are going to be plotting the concentration profile along the tube when we insert a pulse into that tube. So we can start out by drawing our situation here. We know we have one long plug flow reactor here, and so we're going to have 100 perfectly mixed sections. So I'm just going to draw a few here, but we know we'll have more, but they're going to be of equal size, equal volume. Everything about them will be the same physically, except for the concentrations at certain times. And so we're going to be inserting a pulse here of 3 moles per liter. And the way we're going to simulate back mixing is, well, we need to look at the velocity profile. We know that the velocity profile in this tube is going to be this shape here because the liquid that is against the walls of the tube is going to be experiencing friction. And this liquid that's in the center of this tube, the closer it is to the center, the less of that friction it's going to feel, the less slowly it's going to be moving due to that. So not all of our liquid in the tube is moving at the same rate this whole time. So the slower liquid against the walls over here, that is going to be mixing with the previous section of the tube. So that is how this back mixing is occurring. And so when we think about what our concentration is going to look like when we have this rectangular pulse coming in, we can draw that down here. That is going to look like we have a concentration that's going to suddenly drop. It's going to be level at a certain concentration, and then it's going to rise again. And it's going to continue and repeat that. And so we have our nominal inlet flow here of 1 moles per liter. And so that's kind of going to be this state that the concentration is going to keep returning to. And then we have this pulse that we inserted right here, this 3 moles per liter, which is also going to keep returning to. But we know realistically we cannot make concentration immediately increase or decrease like this. We can't make it increase or decrease in the span of no time at all. So more realistically, what these pulses are going to look like is they're going to have some more curves to them. So it's going to be more like this, where it's not a sharp turn there, it's more gradual. And so in order to simulate this in Colab, we're going to need to write out our material balance for each of these individual sections. So in order to plot our concentration profile, we're going to need to know the change in our concentration with respect to time. So we're going to need our dC over dt. We're going to want our concentration times our volume, because the volume of each of these sections is going to be equal and constant. And so our concentration is going to be equal to what's going in versus what's going out. So we know we'll have one flow rate going in. We're going to call that Q in. That's going to be multiplied by the concentration going in. So we'll call that Cn. And then minus what's going out, Q out, times the concentration of what's going out. But when we look at this PFR, there's no accumulation, there's no consumption. The flow rate is really going to be staying the same. So we can say that our Q in is equal to our Q out. So we can rewrite this material balance here, and we can say that our change in concentration with respect to time, and let's move our volume over to the other side to simplify it more, so we'll divide each side by volume. And so our simplified version here will look like our Q in times the differences in our concentrations going in versus out divided by our volume here. So this is going to be the material balance we're going to be using to simulate this in Colab. And then I also want to mention that the way we're going to be modeling how our pulses are behaving right here, the way we're going to be modeling that is by using a sigmoid function. So what a sigmoid looks like is it can only go from the range -1 to 1, and it kind of models this behavior here, this curve, and how it goes gradual lower concentration to the max concentration. And so a sigmoid will look kind of like this, with this being 1 and this being -1 down here. And it doesn't go past that 1 and -1. And you can see this area right here, this curve, will be similar to this. So we can use the sigmoid function to kind of represent how our concentration is actually behaving. And so we're going to be using that function in Colab to model this. So now we can move to Colab. All right, so I have imported our chemical engineering library with all of the libraries that we need for this. And we can start by defining some of our variables. So we know we will want 100 perfectly mixed sections of this tube. So we can say N equals 100. And the total volume of our tube is 100 liters. So we can say our total volume is equal to 100 liters. And then the volume of each individual section of this tube, once we split it up into 100 sections, the volume of each section will be equal to the total volume divided by the number of sections that we want. And then we have our flow of 100 liters per minute, and we have a Cn naught value of 1 moles per liter. And so to define our C naught value, which is going to be our value of every concentration going into each section, we're going to make an array to store all of those values, because it's going to be different for each tank or for each section at different times. So I'm going to do numpy.full, and we want it N by Cn naught. And then we want our Tn to be equal to 10. Press Shift Enter there. And then we want to define our sigmoid function. So we'll just call it sigmoid. And so we want it to be x, and then we want to put in a value here, x naught. And what this is going to allow us to do is shift this function from left to right. So we will set that, we'll set like a value of 0. So it'll default to 0 unless we set it equal to something else. And then we'll also put in a width right here. And what this width will allow us to do is earlier, like I showed on the iPad here, it'll allow us to manipulate how compressed and broadened these jumps and dips in concentration will be. It will allow us to manipulate whether it is a sharp increase or decrease, or whether it is a gradual increase or decrease like this. And then, so we'll set our width, we'll set that default value to 1. And so that will be our sigmoid function, and we want to return scipy dot special dot exp it. We want to return that x minus x naught value over our width. Oops. Okay. And then we also want to define a pulse function. And so we want this pulse function to be in terms of x, and then we want it to have a 0.1 and a 0.2, and then we also want the concentration at 0.1 and the concentration at 0.2. And we're going to set our width equal to 1 as well, I believe. And then we want to return our initial concentration at 0.1 plus our difference in concentration at 0.1 and 2 times this value in our sigmoid. So we want our x, and then we want our x naught to be equal to x1. And we want our width to be equal to width. And so what this term right here represents is that maximum value that our function will reach, that maximum concentration. And so to get the minimum concentration, we're just going to subtract what we just put here. So we're going to say minus that same difference in concentration times our sigmoid at, instead of x naught being x1, we want to shift it to x2. So we're going to say x naught equals x2. And same thing, we're just going to say width equals width. And then I believe we can just press shift enter. Oh, I forgot a colon here. There we go. Right, so shifted my screen over a little bit so we can see the plot we're going to make now. So let's define x to be equal to numpy dot linspace, and then we want it from 0 to 10 and 1000 points there. And then we want to add a plot, so we're going to do fig equals make subplots, and then fig dot add underscore scatter, and we want it to plot our x equal to x and our y to be equal to our pulse function. And so we want it to be x, and then we want our x1 to be at 1, our x2 to be 0.2, and then our concentration 1 we know is going to be our initial inlet concentration of, or concentration of 1 mole per liter. So we're going to say 1, and then we want our C2 to be 4, because again we're doing that 1 moles per liter plus 3 moles per liter of that pulse we're inserting. So that's going to be 4. And then our width, we will set that equal to 0.01 for right now. And then we can press shift enter. What happened? Okay, so it looks like I have a typo right here. I did C2 minus C2, so that's why it's staying at this max value of going back down. So there we go. Okay, so as we can see, there's a very sharp increase in the concentration here and a very sharp decrease. And so, like I said previously, this width right here, that is what's controlling how gradual or not gradual this change in concentration is. So if I change this value here from 0.01 to, let's say, 1, you can see it's a lot more gradual now. So I'm going to change it back to 0.01, but that is basically what that width does. All right, so now we want to solve this balance that we came up with earlier. So we want to define our right-hand side, and we'll do T for time and vec. And we want our Cn to be equal to our pulse function, and then we want T instead of X, and we want it to go 0.1 at 0, 0.2 at 1, and then we want the concentration at 1, we know, to be 1 moles per liter. And then at 0.2, we want it to be 4 moles per liter. And we're going to set our width equal to the same thing I did earlier, 0.01. And then we want C to equal our vec. And so we want our change in concentration to be equal to, we're going to create an array to store all of these changes in concentrations over time in all of these individual tanks. So we're going to do numpy.zeros, and we want an n amount because we have 100 perfectly mixed tanks, and so we want 100 changes in concentration. And so we want to define our first value, dc of 0. And now we're going to come back to our material balance that we derived. And so we can say our Q, our flow rate, times, and then we want our Cn naught, or Cn naught, and then minus our C at 0, all over V. And then we want to define our change in concentrations past that initial value. So we're going to say 1 and on. We want to define as Q times C, and then we want this to go until our second to last term, and we want to subtract C from 1 and on, divided by V. And then we want to return DC. Okay. And sorry, I think this is actually supposed to be, yeah, Cn, because we defined it as Cn up here. And now we want to define n times to be 10 for our plot there, and we're going to say dt equals our Tn divided by n times, so that we get evenly spaced times, or evenly spaced points on our plot. So now we want to define our t-plot to equal numpy.linspace. We want it to go 0 to Tn, and we want it to go n times. And then we actually want to solve our material balance. So we're going to say our results equal scipy.integrate.solve IVP. And we want it to solve our right-hand side from 0 to Tn. And we want our initial concentration to be C naught. And we want our method to be your Dow. Oh, we only need individual quotations for that, actually. And then we want our dense underscore output to equal true. Okay, and then we want to define our C profiles here. We want this to be equal to our res.solve, and then of our t-plot. And now we want to actually plot this. So we will do fig equals make subplots. But so we're actually going to add a loop here because we wanted to plot these changes in concentrations at different points. So we're going to say for t underscore index in range n times. And now we're going to add our plots here. So we're going to do fig dot add scatter. And we want our x to be equal to our array that we did earlier, or the range from n, and we want our y to be equal to our C profiles, all of them into T index. Okay, and then we can say fig to show that. All right. So as we can see here, the first kind of increase in concentration, it goes from 1 to 4, and then it starts to decrease over here. And let's see if we can isolate. Yeah, trace 1 and then trace 2. You can see down here, it's when it starts to increase. So we can see it increases over here. How do I? There we go. And we can see, zoom out here. Maybe not. So we can see that as this starts to decrease, this is starting to increase. And so we could even change our width if we wanted to. Or yeah, up here, say 0.1 instead of 0.01. You can see it gets more gradual. See? Whoa, yeah. So as we increase this width, it's changing how sudden and how steep this change in concentration is. So yeah, that is what our plot looks like. Thank you for watching.